Okay, this video is food and mood, the role of diet and lifestyle in diseases such as anxiety, depression, or really not diseases, symptoms. Depression, anxiety, and some other cognitive mood disorders. Okay, this first image here is of a synapse. So the neuron on top is the presynaptic neuron, and this is a serotonin neuron. The precursor amino acid is tryptophan. It is made into serotonin. The serotonin is stored in vesicles. When the neuron wants to release its neurotransmitter at the synaptic junction here, it'll then have this vesicle fuse with the synaptic cleft, the plasma membrane of the presynaptic neuron. The neurotransmitters are then released into the synaptic cleft. They diffuse across the synaptic cleft to the receptor on the postsynaptic neuron, and this will then activate something in the postsynaptic neuron. Okay. Then the neurotransmitter from the cleft will be taken back up into the presynaptic neuron. Okay. And it will then be degraded by monoamine oxidase type A, so MAOA into 5-HIAA. The point being is the presynaptic neuron will reuptake it. If you want to keep more transmitter in the cleft, what can be done is to give a medication called a serotonin selective reuptake inhibitor, SSRI, and that will then inhibit the reuptake of this neurotransmitter. So that's your typical antidepressant medication. Some tricyclic antidepressants will also have that type of mechanism. So it's good to know that. We're going to be mostly talking about food here, but just to have a little bit of familiarity about these neurotransmitters, that's going to come up a lot. Okay, foods with a potentially negative effect on mood. What optimizes brain function? Well, you got to get adequate sleep. So anything that makes it hard for you to sleep is going to impair brain function. So stimulants, your coffee, your caffeine, your tea, your nicotine and cigarettes, etc. Or, some medications like taking stimulants for attention deficit. Sometimes these things can impair sleep. And what you want is, good ability to focus on whatever you're doing. Having some purpose in life improves brain function. Okay, fine. But what causes decreased brain blood flow? Well, right away, with every meal. Saturated fat causing rouleau formation, sticking the red cells together. The vegetable oils are also going to cause thick blood, increased blood viscosity, blood sludge. Excess sodium is a vasoconstrictor, going to tighten up your arteries so you get less blood supply to your brain. A lack of potassium and magnesium, the things from plants. Excessive stress is also going to impair blood flow. So the point I'm saying is your brain's going to function better. You're going to be in a better mood, have better intellectual energy and vitality if your brain has good blood supply. So all these things, basically the low-fat plant diet gives you what's good for you, and the typical SAD diet, standard American diet, which is high in fat, high in oils, high in sodium, impairs blood supply to your brain. In the long term, that'll cause all kinds of problems. We talked about that before in all the dementia lectures and whatnot. What causes decreased oxygen delivery? Well, the high-fat diet. And, of course, if you're smoking tobacco or abusing opioids or in a carbon monoxide environment, that's bad. People should not be warming up their cars for prolonged amounts of time. I know a lot of young people think that's a cool thing to do. It's not. I mean, you don't have to warm up a car for a prolonged amount of time and potentially be inhaling the carbon monoxide while you're standing around talking to your other friend or person, it's just ignorant. I yell at my kid for doing that, and he just looks at me like I'm an old man who doesn't understand. No, I've been driving quite a few years, and I don't have to warm up my car for, 10 minutes. I think that's stupid. Okay, causes of metabolic decreased glucose delivery. Diabetes, having increased insulin resistance. Everybody thinks about diabetes, about the pancreas, the liver, the skeletal muscle. But the reality is when you've got increased insulin resistance, you impair blood delivery, glucose delivery to your brain, your substantia nigra and your hippocampus. So that's why Alzheimer's is sometimes called type 3 dementia. It's a big deal, okay? I'm sort of giving you preliminary information here, setting the stage, if you will. We're going to get into much more interesting stuff here in just a little bit. Things that cause increased demand. So as you'll recall, this is similar to the concept of what causes dementia. Anything that raises the metabolic demand of a neuron or diminishes the blood supply and glucose delivery, creates a mismatch between what the neuron needs versus what it's getting in terms of oxygen and glucose delivery. There's also plenty of toxins that will inhibit the ability of the neuron to make energy. That's a problem. Stimulants include everything from caffeine, but also monosodium glutate's a potential stimulant of neurons. Same thing with nicotine. Those are going to ramp up the metabolic demand of that neuron. Mercury, for example, inhibits the reuptake of glutamate by astrocytes. Sometimes there'll be an astrocyte, a supporting cell, a glial cell adjacent to the synapse, and that will, with a glutamate synapse, facilitate the uptake of glutamate to get it out of the synaptic cleft. The reason I mention that is it's an excitotoxin, anything that keeps glutamate in the synaptic cleft for a prolonged amount of time. And I really wonder sometimes, is it a safe idea, all these medications that prolong neurotransmitter duration in a synaptic cleft? Do we really understand that neuronal synapse well enough to think it wise on a prolonged basis to be ramping up the duration of time that neurotransmitter sits in there? You know, it was designed the way it is for a reason. Is it wise to do that? That's a secondary question. We're not going to get into that too much right now, but trust me, if you think about neurotransmitters, that comes up, and it's an important one, and hardly anyone's aware of it. Okay, causes of decreased energy production, anything that's inhibiting the mitochondria or energy production. Okay, so review of some stuff real quick. We talked about this. The higher the LDL cholesterol, which is increased by sat fat, also increased by animal protein, the thicker the blood, the higher the blood viscosity. The thicker the blood, the less oxygen delivered to the tissue. Things that stick red blood cells together include IgM antibodies. That's why an acute infection makes your blood prothrombotic. LDL cholesterol, like we said, from eating saturated fat in particular. Omega-6 fats from eating animal protein. Fibrinogen. Fibrinogen goes up with stress, and it's an acute phase reactant, meaning released during a time of acute inflammation or infection by the liver, and it makes your blood more prone to clot. So red blood cells have a negative charge around themselves in their outer, what's called a glycocalyx, and it has a negative charge that repels other red blood cells so they don't stick together. That's a good thing. Bridging molecules like the ones here below, IgM, LDL, fibrinogen, and also uric acid, will cause them to stick together. Okay, rouleau formation is just the red blood cells being stuck together by whatever the bridging molecule. Typical RBC is bigger than a capillary opening. Typical RBC is about 7 microns, capillary opening about 5 microns. So the red blood cells normally, they have to deform a little bit to pass through that capillary. And so when they're all stuck together by rouleau for whatever the reason, LDL cholesterol, for example, or uric acid or IgMs, it's harder for them to get through there, so blood pressure has to go up. As blood pressure goes up, that'll cause injury to arteries and cause more atherosclerosis, which over time diminishes blood flow to tissue and can cause mood problems and impaired cognitive function. Okay, a little bit about how metabolism works. Glucose is taken up into the cell. This will be the plasma membrane here. It's phosphorylated to glucose 6-phosphate. That big phosphate negative charge traps it in the cell. It runs through glycolysis to begin the energy production series of pathways. The end product of glycolysis is pyruvate that then is transported into the mitochondria. This is the center of the mitochondria, mitochondrial matrix. It undergoes Krebs cycle. Each carbon is oxidized to CO2. The electron carriers, NADH, FADH2, are going to go to the inner mitochondrial membrane for electron transport chain, ETC, and oxidative phosphorylation. So that is making ATP while oxygen gets converted into H2O. So here is the electron transport chain in a mitochondria. Outer mitochondrial membrane, usually abbreviated OMM. Inner mitochondrial membrane here. These are the protein complexes within the membrane that do the proton pumping, and they also hand off the electrons. So this will have the weakest attraction to the electrons, complex 1, and then as you go to complex 2, 3, and 4, progressively stronger desire to get those electrons, more electronegativity it's called. And then oxygen here is going to get its electrons and be converted into H2O. In the meantime, protons are pumped by these complexes into the intramembranous space. So intramembranous meaning between the outer and the inner membrane. And you're going to build up a proton gradient there. It's almost like compressed air being pumped into a compressed air container. And then when you hit the button, this is like hitting the button, if you will, the air comes out under pressure. So these protons, it's a real high gradient, like 160 millivolts. They're under tremendous pressure to get back into the inner mitochondrial matrix. So they will zoom across this ATP synthase, complex 5 it's sometimes called, and that energizes it to convert ADP into ATP. And that's how most energy is made in the human body. There's all kinds of things that will inhibit these complexes. So anything that's markedly inhibiting the energy production in the inner mitochondrial membrane here will decrease the cell's ability to meet its energy demands. And that ends up being really important. It's thought to be like the most common cause of aging, cancer, and death. Okay, so it's kind of like good to know about it. Okay, here's an example of lipid peroxidation. For example, if somebody eats a high-fat diet, the high fat will have a tendency to send too many FADH2 electron carriers to the inner mitochondrial membrane, and it'll overwhelm complex 3 in particular, and then the electron transport will start to back up. This is what causes insulin resistance with diabetes, excessive dietary fat getting into the mitochondrial membrane, and it's not able to regulate it as well as it can regulate the glucose. So the skeletal muscle, this begins in the skeletal muscle, and then it's going to cascade into other parts of the body. So when electron transport reverses, an enzyme will drop down from complex 3, typically, or coenzyme Q, down to oxygen, and it'll convert it into a free radical called superoxide. Most of the superoxides neutralize very quickly by superoxide dismutase, okay? Hydrogen peroxide is produced, and this will sometimes get converted if it's present, only if it's present in excessive amounts. Usually the cell controls it well. But when a person eats tons of fat on a daily basis, day after day, several high-fat meals a day, you're going to have excessive amounts of this. You're going to have depletion of your antioxidants, and you're going to sometimes end up running this Fenton reaction, which is going to produce hydroxyl radical. Hydroxyl radical then will often interact with the adjacent inner mitochondrial membrane and damage it through what is called lipid peroxidation. So the reason I'm going through all this is understanding that this is what's happening in your body. This is what's destroying the ability of your brain cells to make energy. You want to avoid high-fat diets. Okay, that's like one of the most important things you can learn, because they just lead to deterioration over time. And as you get older, you got less ability to compensate, and you just keep losing brain cells. You're going to become stupider and eventually demented. Okay, here's a bunch of things that inhibit, some things that inhibit glycolysis. That's AS for arsenic, F-. Traumatic brain injury inhibits pyruvate dehydrogenase. We'll talk about traumatic brain injury in a different lecture, but just know that it inhibits pyruvate dehydrogenase. Patients with TBI, traumatic brain injury, they need time off. They can't just go back in the game right away. Their brain needs some time to heal. Okay, mitochondrial inhibitors, there's a whole bunch of them. Here's just a list of them. Here's a diagram showing some of these mitochondrial inhibitors. Like here's GP, that's damaging to complex 2, cadmium to complex 3, high-fat diet we talked about in particular impairs complex 3 function. So you avoid these things as best you can. Some of them, you avoid GP by only eat organic food. Okay, you avoid F- by, have a reverse osmosis in your kitchen, preferably have a well water without F- in the water. But these are some of the things that are impairing your oxygen delivery. So it's all a multifactorial process. You want to optimize your energy production so you can handle whatever metabolic demand your neurons have. You want to avoid these toxins, and then you want to avoid unnecessary stimulants that ramp up your demand for no good reason. Okay, so a little more on food and mood. An emotion is something transient that'll come and go over minutes to hours, caused by your life events. You'll know what caused it. A mood is longer lasting, and a lot of times you can't even tell what caused it. That's from hours to days. And then a personality is sort of a person's disposition and attitude, and that can be relatively fixed for years or decades. Things that cause anxiety and insomnia, we talked about that, of course, caffeine, but MSG can do it as well. Nicotine, alcohol in its own way. Alcohol is kind of a mixed bag, but it does cause insomnia as well. Too much exposure to bright lights in the evening, you're not going to make as much melatonin as you should. Sleep apnea make you hypoxic and impair your sleep recuperative ability. What causes depression? So now here are theories of depression, and just like theories of cancer, this is a really important idea. Now, for example, for cancer, if you only think the genetic cause of cancer, you're really not going to make any progress. You start thinking about the metabolic cause of cancer, you'll all of a sudden understand all kinds of things that could really help you a lot. With depression, it's multifactorial. And yeah, a lot of times people have a sad life event, and that sort of tips them over the edge. I was sad when my mom died, okay? People are sad when something important to them It doesn't go well. So that's totally understandable. But it's worse if the person's very socially isolated with no one to talk to. It's worse if they feel they have no hope. Okay? Now, the food theory, like we're talking about here, is the way bad diet causes brain tissue hypoxia, hypoglycemia, excitotoxicity, mitochondrial toxicity, all those things that are decreasing the brain's energy or ability to meet its needs are going to predispose a person to bad moods, brain fog, anxiety, and other problems. Additional theories of depression, genetic theory, some people are predisposed, maybe, but I think that's kind of a weak component. Personality theory, because of their personality, how pessimistic they are. Yeah, fine, but it's not really our topic. It's not that big. Environmental theory, negative life events, social isolation. Okay. Religious theory, that a person's happier when they feel that life has meaning and they have purpose in their life. That's fine. That's a helpful thing, but it's not our main point. Hormonal theory is largely along the lines of stress and excessive cortisol, because that's going to do a lot of bad things to the brain. When it's constantly high, it'll impair neurogenesis, learning. It'll be decreased dendrite complexity. So that's not good. We'll come back to the effect of stress a little later and stress equivalents. Comorbidity theory just means that when somebody has other illnesses, they're sad because they're sick. Hypothyroidism can impair cognitive performance and mood. Traumatic brain injury. So these are comorbid, just means other diseases they have in addition to whatever's happening with their brain. Sometimes people are sad because they got an arthritis, like rheumatoid arthritis, or they got a shoulder problem and they can't sleep. Okay, the big one, though, for our purposes here to talk about is monoamine theory, and that's sort of dominated depression and depression treatment for the last couple of decades. And that's the idea that there's a so-called neurotransmitter imbalance, a lack of a neurotransmitter, and the person needs a pill to increase the presence of that neurotransmitter in their brain synapses, let's say serotonin, like the one we showed at the beginning, in order to improve their mood. There's a lot of controversy about that. Some people say, well, those medications work well in the short term, and that might very well be true. Other people say, well, they may well work well in the short term for some people, but they don't tend to work well in the long term for most people. These are some of the popular opinions amongst psychiatrists, experts on the subject. And they got the potential for side effects. Like I said, I wonder, is it really a wise idea to be inhibiting your synaptic reuptake of a neurotransmitter? What's that going to be, its effect long term on that postsynaptic neuron? Okay, cytokine inflammatory theory. And so right now the monoamine theory is sort of fading into being considered less important than previously because the scientific data has not been that great to support it. There are people who claim that the antidepressants, even the newer ones, really are not that much better than placebo, especially not in the long term. And there's studies, so that's sort of a specialty topic, and it's not really the focus of this, but I'm just letting you know they're not that great. And they can even have very severe side effects. A lot of people who behave in a crazy way out of character for their past, it's because they're on these types of medications. The big hot new topic in depression is cytokine inflammation theory. So the monoamine theory is really shown not to have panned out as well as people had thought it would, and they can't measure the neurotransmitter in a person's brain. The pills, SSRIs, TCAs, don't work as well as they were initially thought to work. So now there's all this interest in the cytokine inflammation theory as a cause of depression. And this is really a big sentence right here in this talk. I think you're going to find this amusing. Okay, so the big thing being promoted now is that elevated blood tests for CRP, C-reactive protein, is associated with increased risk of depression, and it's considered an indicator of inflammation. And the reason why I find that funny is because eating a high-fat meal causes elevated CRP. And you look at some of the research experts like Gregory Sloop, MD, he's probably the best atherosclerosis researcher in the world. He says CRP is not necessarily indicative of inflammation. He says it indicates that the muscle's not able to replenish its glycogen because of the thick blood from rouleau formation, and that its release is, in a sense, myokine, muscle signaling that it's signaling that it needs help getting its glycogen reestablished within the skeletal muscle. So the point I'm making is it's claimed to be inflammatory, so they're going to recommend all these anti-inflammatory drugs. But according to a lot of experts, it's really just a problem of high-fat diet. So fix the diet and you fix the problem. You don't need to take some anti-inflammatory drug. So that's an interesting thing. Okay, we talked a little bit in some of the other lectures like about excitotoxins and sodium that normally you should be eating at least 5 to 1, preferably more like about 10 to 1, 10 times as much potassium as sodium. Okay, this is the Latin, kalium in Latin for potassium, natrium in Latin for sodium. And normally if you're eating about 10 to 1 potassium, your ion gradients in your plasma membrane of cells will be just what you want them to be. Magnesium is also in the center of chlorophyll. You get plenty of that from eating plants. What happens if you're eating a lot of processed food is your diet will be very high in sodium, and it's going to disrupt this plasma membrane pump. This is the potassium sodium ATPase pump to maintain, your negative 65 millivolts in your cells, like in your neurons, for example. And the net result of excessive dietary sodium is you get high sodium inside the cell, leading to inability to run the calcium pumps, and then you start getting high calcium in your cells. High calcium in cells leads to high blood pressure. It also leads to excitotoxicity. Sorry about the dogs. Excitotoxicity in your neurons of your brain, and that can cause anxiety. So that's it for this lecture. We'll talk more about this in part 2. And that's just the serotonin synapse.